Newton's second law on inclines, example number 2. Here we have a 5 kilogram block on a ramp that can be inclined at any angle. We don't know what the angle is. Once again, I'm not drawing the ramp, but there's going to be some angle. This one does have friction, but here's our generic diagram of the three forces, actually two forces, but the one resolved into two components. The weight normal, which will be equal to the normal force of the ramp, and then the weight parallel. But then there also will be, if this thing is impending, it's about ready to slide down. It's not sliding down yet, but friction is going to match the weight parallel up to a point. Friction has a maximum. So right now, we're not sliding yet, but we have a force of friction that is a static friction at this point that I will calculate here in a few minutes. But one of the first things you want to do with these problems is deal with this W sub n and W sub p in the generic. So I will draw my weight vector straight down, and I know W is going to be 50 newtons, but I'm just going to symbolize it right now. Later on I'll put the actual numerical value in, because I'm going to have W sub n and W sub p, W sub n, and then we have our angle theta right here. I'm going to do this symbolically at first, and it goes like this. The sine, or let's do cosine, doesn't matter. Cosine of theta will be equal to W sub n over W, and it always turns out this way. So W sub n will be W cosine theta. It happens every time like that. And then, as you'll see here, it's going to be W sub p will be W sine theta, but I'll write it all out again. Eventually, you can stop this initial step here, because it always comes out as Wn equals W cosine theta. But here we have sine of theta is W sub p over W, and then W sub p always comes out as W sine theta. That says sine theta there. The S didn't come out too well. Let me try fix that. Okay. All right, so we're going to hang on to those. We'll plug numbers in later. But we also know now in this first part, part A, once again, the nice thing about part A here is that the acceleration equals 0. It's not moving yet. F net equals 0. Therefore, the forces are all balanced. We always know that W sub n and F sub n are always equal on these ramp problems. But here, if it's not moving, but it's just about ready to move. But we know that F net is 0, so we know that W sub p is equal to the force of friction. Now we're going to start substituting. We know that W sub p over here on the right-hand side is W sine theta, but the force of friction is going to be the coefficient, mu, times the normal force. So the force of friction is mu, which we do know in this case is static. It's 0.35, but I'm not even going to plug that in yet. I'm going to do everything symbolic. Mu times F sub n. Well, force normal is equal to weight normal, so the weight normal is W cosine theta. I'm going to plug that in for the force of friction over here. I'm also going to plug in the W sub p. The W sub p I'm going to plug in to there, and we'll get something of this nature. It's going to be W sine theta equals mu times W cosine theta. And if you're looking at the math here already, some interesting things happen. You're going to see that the W is going to cancel out because these are terms on both sides. There's no addition or subtraction. They're just factors, I should say, on both sides. So the W's are going to cancel out. You can divide both sides by W. And if you move the cosine over, let me see if I can move things around here. All right, so I move this up. You get mu equals sine of theta over the cosine of theta. And from a mathematical standpoint, for me, that just kind of warms my little heart because it's just kind of fun to cross out the W's and come up with a simple statement here, simple equation, that mu is equal to sine theta over cosine theta. And even better yet, if you remember from trigonometry, which you may not have gotten that far yet, but I'll just tell you, it doesn't really matter whether you do this or not, mu equals tangent of theta, because sine over cosine is tangent. Actually, that is a pretty important step here, but it's a very simple equation we have here now. In other words, we know what mu is, so we can calculate theta. It's a very simple mathematical operation here. Mu was given as 0.35, so we have 0.35 equals the tangent of theta. So if you do inverse tangent on a 0.35, you end up with the theta, in this particular case, for this ramp, of 19 degrees. So this thing will start to slide, just barely start to slide at 19 degrees. Anything beyond that, it'll accelerate. At that point, it breaks loose. And after it breaks loose, we will have kinetic friction. Now let me switch to a different color here. I'll go back to red. So part B, it's now going to accelerate because the force of friction will be less than it was in the first case. Well, let's figure out the force of friction and all the other quantities now numerically. For example, the force of friction in part B here will be mu, the kinetic frictional force, times F sub n. Now F sub n is going to be equal to W sub n. So we have to get W sub n. And we can do that off to the side over here. If you look at the top, W sub n equals W times cosine of theta. Let me plug these in here. W sub n will be equal to, well, the weight is 50. 5 times 10. It's 5 kilograms of mass times 10 for the acceleration due to gravity times the cosine of 19. Now we're assuming we're staying at the 19-degree angle. So W sub n is 50 times the cosine of 19 degrees. So that's 47 newtons. Therefore, if we plug that in over here back up to the top, the force of friction will be equal to mu, kinetic mu, which is 0.25 times the 47, going to 2 sig figs. The force of friction will be 12 newtons. All right, that's an important number. It's not the answer, but I'll put a little box around that. And that's also going to be restricting the motion, but what's actually trying to make the object accelerate down the ramp is the W sub p. So I'm going to calculate W sub p. W sub p is going to be W sine theta. So it's going to be 50 times the sine of theta. That's from, which is 19 degrees. That's 19 degrees there. 50 times the sine of 19. Once again, it's still the same angle. So W sub p, the force trying to make the box accelerate down the ramp, is 16 newtons. So that's important. The two boxes right now here in red are the important ones, because now I'm going to apply F net equals ma. I'll switch colors again. I'll use blue. So F net equals ma. F net equals ma for the blocks in the direction down the ramp. So the 16 newtons W sub p is pulling down. It's the bigger force minus the smaller force. So I'll have the bigger force 16 minus the restricting force of friction 12 equals the mass, which is 5 times a. So if you do the math here, 16 minus 12 is 4 divided by 5. The acceleration is 0.8 meters per second squared. And that will be the rate of acceleration for this box down the ramp.